Uh, right. So what I want to do is go through R in about 60 minutes. And the idea here is, I assume that you have some knowledge of R. Who doesn't know R at all? Just so we know. It's okay, no shame. One, two. All right, so most of you know some of R. For some it will be a discovery. And if you know R, you probably know that mostly working with R is like magic. You know, you have a spell that you've learned, and mostly it works, and then when it doesn't, there's very little to do about it, right? You have, very little help. It reminds me of this quote from Arthur C. Clarke, which said that any technology advanced enough is indistinguishable from magic. So the goal of this lecture is to sort of remove the veil and try to give you a mental model of what R does behind the scenes, so that maybe you can better understand what's going on, and what, for instance, what went wrong with that particular spell. To do this, I want to, right. To do this, I will, and some of the things I'm saying are very are only going to scratch the surface. We have a number of other lectures that will go into depth. So this is just an overview. So, and you have all of this text on your flash drive. It comes as a markdown file, which you can compile, or as an HTML. All right. So where does R come from? Why R? So R comes from S. S was a language developed at AT&T Bell Labs. And the reason people developed S was very simple. They had a large number of statistical routines that they liked a lot, which were written in the programming language Fortran. Maybe you haven't programmed in Fortran. Probably you're lucky. It's not the funnest programming language to use. And what people minded was that they were doing the same thing over again. They wanted to do a simple analysis, so they had to write code to read in the data into Fortran, to change the data to the format that the routine wanted, then to write the data out once the routine had done its work. And they were doing that over and over again. Said, this is horrible. We want to do something better. We want a glue language that will allow us to not have to write all of that boilerplate code. And that's how the idea of S started, as a glue language that would get exploratory data analysis to run faster. And by run faster, I mean people would develop code quicker. And S was a success. People picked it up. Eventually, people started writing actual statistical code in S. It wasn't just for gluing existing libraries. People started writing real analysis in S. Then AT&T spun off the project, became a commercial enterprise, and at some point around 94-ish, if you could join up with someone, I paired everybody up, so find a couple of people or maybe a trio to join. There will be some questions later. So AT&T spun off the project, and around 95, Ross Ihaka and Robert Gentleman, who were in New Zealand, decided to develop a new statistical language, which they called R. And eventually, R became essentially the successor of S. It was cleaner, faster, and most importantly, it was released in open source license. It was the main thing. S was a commercial product owned by AT&T and its subsidiaries. R came out under GPL license, which means that anything you build with R has to remain public. Right? R has been designed so nobody could steal it from the authors of the language. And that's a really big thing. Which is also a problem, because some companies actually want to develop products around R. And the question is, how do you do that if every piece of code you write has to be put back in the public domain? So there are ways, but it's tricky. So why do we talk about R? Well, it's the language that is most widely used for data analysis. It's becoming a very popular language. I've got quotes there that say that amongst some ranking, R is the 5th most popular language, and another ranking puts it in the 12th position. I mean, these are not particularly scientific studies, but the point here is that R's importance has been growing fairly quickly, and it's used in pretty much everywhere. A couple of years ago, I was visiting Netflix. Netflix has a huge stable of statisticians that are working in R. They develop techniques and algorithms. And then when Netflix wants to put them in production, there's another team of computer scientists and software engineers that recodes the algorithm in Java and then runs them on top of MapReduce. Okay? Not the best development process, but R is central. All right. So this is why we want to look at R. So what I want to do is try to emphasize. So the goals of the R and S design was to build a language that is as flexible as possible. That a language that allows you to define new abstractions and that build on those as if they were part of the language. So what I want to do is show you how to build abstractions in R. What are the basic building blocks that are bolted in the language, and what we can construct on top of those building blocks. So for that, I will use a slightly different order of presentation than you will find in most books, because I'll start really with the fundamental elements that make up the language, and then we'll grow up to the point where we can actually implement statistical routines. So, just that around. So, and what I want to do is do a bit of live coding. So I'll be switching between my R Studio session and the slides. Of course, anytime you want to interrupt with a question, please do. Does everybody have that file now? Yes, we're passing it. Okay, good. So what are the basic building blocks of the language? The first thing that R had from the start is the notion of functions and function calls. So what they wanted to do was call these Fortran routines, so they have to build that at least in the language. So here's a bit of R code, right? So this is defining a function that takes an argument y, adds 1 to y, and returns that value. So in R, you don't need to write a return statement here. The last thing that the function does is the value of the function. So if we run this, we'll get an exciting result. The value 2 is printed here. But the interesting thing is we've done two things here. We have created a function object. So this is a value in the language. We have bound it to the variable f, and then we have called it. Okay? So a function is this keyword function, its argument list, and a body. And that's always the case in R. The body may have braces if you want to do more than one thing, and if there's only a single expression, you can remove the braces. So for instance, I could have just as well deleted this and the same thing happens, right? Okay. So what else is there to know about functions? So the shortest function in the book is the function that has an empty body, empty argument list, and a body that is, say, just a constant one. This is not a useful function, but it's a well-defined one. Functions can have multiple multiple statements, like with a semicolon here, we're assigning to a local variable y, and then we return adding the addition of 1. And functions, more interestingly, can have fairly rich argument lists. So here is a function that has at least one argument, x. Then the dot dot here means it can have any number of other arguments. And then there's an argument named y at the end. So in R, the way to think of this declaration is, this is a function that will at least take one argument, but that argument, even if you don't pass it, it's still okay because you've provided a default value in case you don't give the argument to f of 0. Then there's a list, possibly many arguments, and then there's one argument hanging off the end here, which is can only be passed by name, and I'll tell you more about this. And the body of the function here says, if you've passed in anything into the dot dot dot, if length of this dot 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 is zero, do one thing. If it's not 0, do the other. Okay. So. Yep.
Why do you assign
this is, so I think this is a little bit too, let me just get more on the screen.
I understand that assignments have an invisible return.
Let me just one sec. I'll format it a little bit better, so it will be nicer to read. And so what I'm doing here is two things. I'm taking this dot 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 and turning it into a list. Thing number 1. Checking, I assign it to z. Well, it's 3 things. I assign it to z, so I can use that later. And I check whether the length of this list is 0. If the length of this list is 0, that means nobody passed extra arguments. If it's not, somebody did. So if it's 0, I just multiply x and y. If it is not 0, now I have a valid z, and I can access the first element of that list.
So it doesn't look like the 0 is in the right position.
Isn't it? Which one? This one?
The equals 0 is inside the length of the function call.
Oh, that may be a typo. Yeah, that looks like a typo. Let's see what happens if we run it. So let's see. I may have made a typo. Yeah, that looks like a typo. So chuck. So I want length. I want it here, right? Okay, so will that be happier? Oh yeah, that should be in one. Let me put braces around it because it's sometimes finicky when you paste code in the window. Copy, paste. Yeah, much happier. So yeah, you're right. That was a typo there. So does that make it clearer?
Yeah, and I thought that if you do a variable argument parameter in a function, it already is a list. But if it's not, then what data type is it?
My understanding is it's something that gets expanded magically by the implementation. So it's not a data type, but I may be wrong on this part. So what we can do is just, let me say, let me define this into a proper function. I assign it to f, and I print dot dot dot. Let's try that for start. Will that work? F1, 2, 3. That worked. So now I can say type of dot dot dot. Type of dot dot dot, and try again. Yeah. So it didn't like. So that's a bit of magic. And in order to access the dot dot dot, the pattern that I know is you turn it into a list. So there are two ways you can use dot dot dot. You can pass it to another function call, in which case it will be passed down to that function. Or in that particular case, this is also passing it to a function call. It gets expanded in a list of arguments, and list then turns it into a proper list that you can access. Okay? So, all right. So calling these functions can be done as follows. So I can call f with nothing, right? I gave it these default arguments, so it's completely fine to call it with nothing. It will take the default arguments I've passed it. So if I call f with nothing, it will take 0 for this one, nothing for this, and 2 for that. Make sense? I can call it with 2 arguments, 1, 2. I can call a function by giving the name of the arguments, x and y. I can give the names in any order I want, y and x, right? I don't have to use the name of a function here. I could store a function in a vector, get that function of the vector, and then call it. That's all fine as function calls go. Okay. So, any questions on this so far? So the idea in R was that functions can have many arguments. You know, the largest function signatures I've seen has 25. So 25 arguments, there's no way you can remember the order and what they are. So this is why you can pass them by name. And this is why these arguments typically tend to have default values. Because if you forget one, there's probably a reasonable default that we can set. And that makes life much easier. So you just pass the arguments that you need. Everything else you say, you know, let's hope there's a valid default. If there isn't, somebody will complain.
What are the x index 42, x equals 1?
Okay, so I'll show you that one. That's easy. So x42, well, let me just do that. I'll take, come on, beep, 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 beep. x42, well, 242, what say you about that? So that didn't work. Square brackets are, but that should work. So let's see, did I, function object xxx not found. So xx equals null. Did I have no xx? Type line closure, zeroid vector allocation. Buh. I'm going to say, let's see, xx, I'm just, I wanted to show it easily, but let me not get stuck on this. So you can store functions. Functions are values. You can store them in data structures, like in an environment or a list. This is just saying retrieve the function from some data structure, get me a function, and then call it. That's the point I want to show here. So there's fun to be had. here's fun. So in R, plus, open paren are functions, like anything. So here I can define my own version of plus. And what does my own version of plus do? It concatenates the argument as strings. I can define my own version of paren. And what does my version of paren do? It prints the argument with parentheses around. Okay? So now I can run 1 plus 1. Let's see what happens. All right, so if I run 1 plus 1, I get 2. Actually, I get twice 1, but not really what you would have expected, right? Because I've redefined plus to be string, to turn its arguments into string and concatenate them. And I redefine the paren to just print this out. Do you want to do this? No, you don't, right? It's silly, but you know you can. And actually, there is code that redefines the paren in some of Hadley-Wickham's packages. So, you know, if you want to see craziness, hello, that's a good place to start. All right. I'll skip this. So I have some exercises, but I'll probably skip them from time to time. So once you've messed up your environment and redefined plus and paren, you probably want to delete those definitions. So this will do the job, because otherwise anything that wants to do an addition will not work. So poof, gone. So that's good to know. You can recover from accidents. So let's see. What did I want to say here? I don't know. So the last bit about functions that I wanted to make was, I showed you this syntax where you can have some arguments, then dot dot, and then another argument. The way to use these is you can also use them in vectors. So the function C creates a vector, and you know this is take the optional arguments, turn them into vector, store them into L1. This is take X and the optional argument. This is take Y, the optional argument, and X. Create 3 vectors. Then index the first vector at 1, index the second vector at 2, the third vector at 3, and return the sum of these values.
Just using the optional arguments ellipsis allow you to include an arbitrary number of optional?
Yes. So you can absolutely do that. So I could write, 3, 4, 5 in that call. Any number. I mean, any number may be a bit optimistic, but any number you feel like typing will probably work. So here's a question that I would like you to think about and try to solve in teams. If I call f with 1, 2, 3, what will be the answer? There will be a number printed. It will be the sum of the first element of L1, the second element of L2, the third element of L3. What is that sum? One way you can do it, you could just run this in your browser. It's kind of cheating, but that's fine too. So think about it, talk about it. I'll give you a minute to think about it, talk about it between yourselves, and then we will proceed.
Now what I'm curious
All right? Doesn't have to be a full answer. I just wanted you to think about this for a little bit. So, what is L1? L1 is the list of arguments that are in the dot, dot, dot. What is the list? It's the number 2. So L1 is a vector with 2. What is L2? It's the first argument, x, and the dot, dot, dot. So it's 1, 2. What is L3? It's the last argument, 3, the dot, 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 2, and the x, 1. So 3 to 1, and so we're adding 2, 2, and 1, which must be like 7 or something. Yeah, my math doesn't work so well. 5. I noted it down before and I ran it. But, okay. All right. So does that make sense? Yeah. So the cool thing about this is the only way to pass the last argument, the y, is by name. Because R doesn't know how many dots, how many things are going in dot, dot, dot. So the only way you can tell it, give it a value for y, is if you name y. You have to say y equal.
Or if you put it before the x.
Sorry?
Or if you put it before the ellipses.
You still have to say it's y. How does it know it's before the ellipses?
No, but if it's like x, comma, y, if in the function definition, then forever.
Oh, yes. But they put it here for a very good reason. Because you want this to be like, an optional parameter you don't usually change. This is like a special position that makes it harder to pass. Okay. And there's a good reason why you would do this software engineering-wise. So these are the things that typically don't change. So you stuff them behind there, they're kind of hidden.
And usually they have a default value then to make
yeah, you would, otherwise it kind of defeats the purpose.
So is this actually good coding practice to do something like this? Because if I remove the y equals 3,
yeah.
I just remove the y equals, I get a totally different result, even though my arguments in the function code is the same.
So
somehow it's weird.
So if you remove the y, so it is weird, and it only makes sense if this is something you expect not to change often. Like, I don't know, a graphic device, and the default is really good, or that is my understanding of the usage pattern. But in this particular function, if you happen to not pass y, the code will break because here you will have an undefined argument, and that will be unlucky. So, so how do functions evaluate? They run through the statements of the body until they get to the end, and whatever is at the end, the value is returned to you. There's 2 ways to change that in R. You can have a return statement, which returns earlier, before you've gone to the end of a function, or you can call stop. Stop is like an exception handling mechanism. It just gets out of the current function, and then you can catch a stop at some other point. So for instance, here is an example of a stop, where we're saying stop with an exception, and then it's just nested in a catch, which catches that exception. It's not a very interesting piece of code, but yeah, it does show something. So the question here was, what happens if we call it with f minus 1? Well, we can try it. Any suggestions? Oops. So I lied a little bit. I said that a function only ends when it runs to the end of its body. There's another way for a function to die, which is if you have infinite recursion. And this is what was happening here. It's not infinite, we'll get to it. But so here we have a function f, which if x is fx equals 0 stops. If it's not equal to 0, decrements x by 1. Okay? If I call it with -1, we'll just decrement till infinity. Now, we don't decrement till infinity because numbers have a finite range, but we don't even get to the end of that range because the implementation of R has a hard limit. There's only so many calls you can have. Why is that? Because every time you call a function, you put a little bit of data into a data structure called the stack. So you put the arguments to the function on this stack. So each time you call a function, you use a little bit of memory, and there's a point where you don't have enough memory in the stack, and that is the point where R complains and stops the execution. So this is a limit that can be changed, but if you hit it, most likely what you're doing is wrong. Most likely you have a infinite recursion. The only valid case where this would not be true is if you were, for instance, doing some kind of, if you had a huge graph and you had a function that does graph traversal recursively, maybe you would get that limit in a normal case, but usually it's a mistake. Okay.
So
Yeah.
we actually get different errors.
Yep.
Instead of C-stack,
Yeah.
he gets the C-stack error.
Yep.
We get the error evaluation nested to deeply, infinite recursion, options, etc. Is there
Right. So which version of R are you running?
simple functions or something?
Yes. And now which version are you running? Yes. The whatever the name of it is funny. Darkness prevails or something like that. So they've changed so the way R works was changed in a fairly major way between 3.3 and 3.4. So in 3.3, they had an interpreter that was essentially using a linked list for the stack. And now they have a bytecode interpreter that uses the C stack, that is the underlying, closer to the hardware stack. So you will get different error messages, same symptom. Yeah. You get what? Yes, because that implementation was already there, but it was optional. So depending on how you switch it, before 3.4 you could see that or not. Now you always see that. It's not confusing at all. All right, so we went through the first bit of R that is sort of foundational, which is function calls. We know what functions are. So the next bit that is just as important is environments. So environments are typically not something you see in intro courses on R, but they are just as important, and they're the building blocks of everything else. So we will present them. So an environment is like a mapping between names and values. A mapping between names and values. So if I create an environment here, I store it into E, I can store things into it. So I can store, I can map name A to false, B to string A, C to a number, D to a vector. Okay, so let me run this for you, and we'll see how that works. Yeah, thank you. I saw that. So, what is E? So if I type out E, it says environment. And now, what can I do with the environment? I can ask questions. I can say, what is the value of A? It's false. What is the value of B? It's the string A. And I can also ask questions that have no answer. If I say, what is the value of X, Y, Z? Well, that should not have an answer because I didn't put anything into X, Y, Z. And it says null. Okay? So the environment is a mapping from name to values. And the environment is crucial because that is, in a function, that is where you store your local variables. That is where you store your arguments. At the top level, that's where you store all the definition we type in the console. So environments are used everywhere, and they're really handy data structures.
How is as a data structure new environment any different from a
Uh,
Seems like it's the same.
So the question is how is a new environment different from a list? The internal implementation of an environment is likely to differ. So I'll get to the list in a little bit, but let's just think, if you know what a hash map is, or a hash table, this is what is used in an environment. So they want to have very fast access to the variables. In a list, if I'm looking up for something, I have to go through the list, find that thing. So if the list is really long, well, time is time of traversing the entire list. With a hash map, you just jump where you hope it is.
Can you attach new environments in the same way you can attach data structures so environments happen automatically?
So in R, you can attach a data structure. So you can attach a list, and that means all of the names in that list suddenly become part of your current scope. Let's see. So I don't know, but I'm happy to try it out. Come on. Somebody should tell the designers of RStudio that the focus is wrong. Attach E. Okay, so now I can say, no, that's so, think partly successful. D, so what happened when I attached the environment is some of the variables in the environment existed already in my global, and these I can't see, but the other ones I can access. So for instance, here I have D and C, which have the values that I gave them. A and B are from the global environment.
Did you use the name list?
Can't you explicitly access those maps by saying from this environment, though?
Well, I can do this, right? I can do $A.
Yeah, so
That's
even if
fine.
it's matched, you can still
Yeah.
access it.
Yeah. Okay, so the answer is yes, you can. All right. So here's the pictorial representation of an environment. It's got these names, and then outside of the environment, it has pointers to these values that float in the computer's memory, right? And you can keep adding names on as long as you want. The environment will grow as needed. You can shrink an environment by removing things from it. That also works. But it gets more interesting because environments have a structure. Each environment has a parent. And when you look up names, you can look up names through that chains of environments. So how can I explain this? So here's a bit of code that shows how to get this to work. So I create a new environment F. Remember, I had an old environment E that I had populated, and I set the parent of F to be E. So now I have two environments. There's a parent relationship between them. I can look up, and F is empty. I didn't put any names into it. I can look up the name C in F. What will happen is we'll see that F is empty, and then go to E, find the value of C, print it. All right. So why is this important? Because this is the way R builds in namespaces, packages, function scopes. Everything is built on top of this mechanism, of this chaining of environments. So understanding this helps you understand how names are looked up. So if I'm inside a function, I look up in my local environment. If I don't find it there, if that function was defined in an enclosing function, I look up in the enclosing function. If I don't find the name there, I look up in my global namespace. If I don't find it there, I look up in the packages that I've loaded, and so on. So that's this chaining of environment. So for instance, as a fun exercise for you, what if I write F parent, 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 parent? It's kind of looking weird. That's a weird looking expression, but it does something. What should I expect? So first, let me explain to you what this syntax does. So the function f here is a function, which I can call, and its last expression is a function. So it's a function that returns a new function. So when I call f here, what do I get? I get a function, which I can call again, right? Get a function, I call that function. All right. So, what does the function do? It returns x. X here is defined to 42. X is defined at minus 42. This is 42. Which one will this return is the question. And I'll give you 30 seconds to discuss this in groups, and then raise your hand if you know. All right. Sure. So, anybody? Suggestions? Who's for 42? Minus 42? Okay, we're split. Good. So, it's actually interesting because this is exactly the difference between S and R. So, the old language S came from Lisp. In the old version of Lisp, the answer was minus 42 because it was doing dynamic lookup, and that was in the scope. R is lexically scoped, so this function has an environment. The parent environment of that function is this environment. The parent environment of this function is the global. So we will look up x first in the enclosing. We find it, we're good. If we didn't find it, we would look up in the global, and then we would find minus 42. All right?
But aren't you calling? My understanding is that the function returns an anonymous function.
Yes.
And then calls x. And then says, well, what's the
Value of the anonymous function asks what's the value of x, yes?
I guess I thought the way that I interpret it is that f is going to return a function of the object
Yeah.
x, just return the object x. But then it's going to be resolved in that second set of parentheses is going to be resolving the anonymous function that's in the global environment.
So here's how it works. When we call the first f, what we do is we create an environment where x is defined, and then we create a function, a new function, that has a pointer to that environment. Then f returns. So we forget about it. But the environment that we created for f still lives. What we have in our hands is this function, which has as its body just this, hey, tell me what the variable value of x is. And it has its own environment, and it has the enclosing environment of the function that created, which is still around in memory, even though the function has returned.
So even though so that function that's created sort of carries a context.
Yes, it carries that memory. So whenever you do nested function, you have to realize that you're keeping around alive all of the data that surrounded it in its scope. And that's typically a good thing, but sometimes it can be also a source of memory leaks because suddenly you have lots of space and you don't know why that thing is around. So that's
because you created something now. And
still, this guy lives as long as this guy.
So
So let's run it to make sure that I'm not lying. Never trust anyone. You know, you're data people, so check it. So let's see. F, open parent Chuck. If I just do F with one step of parent, what does it say? Oh, this is a function, and the function S, and it has an environment. And if we looked at an environment, it would tell us it has a parent. So I can call that thing again, and I get 42. All right. Cool. the cool thing about environment is they're used everywhere. So they're used, as I quickly alluded to, in namespaces. So when you load a package, the package brings a set of names of functions, and they're stored in an environment. So there's a fairly complex structure, and I'll just allude to it here. I won't tell you much about, but if I have my, so the structure is this. There's, say, the stats package. That's the package that has the function SD for standard deviation. So if I load the stat package, I will create an environment for that stats package, and all the functions of the stat package are there. And they're function objects, these data structures that have the code, and they live in memory too, and they point to that namespace. When I load the stats package, it also has some imports, other packages it needs. So it will create a namespace for the things it imports. It will have the base namespace where all of the standard definitions are, and it will then also connect to the global environment. This is where what you write in the console is. When your code loads a package, it loads this after the global environment. And this is like maybe a sequence of packages you've loaded. And at the end, you have what is called the base environment, where there's the default function that are always there in R, and the empty environment. So if I type SD in my console, if I type SD, what happens? Well, I get this function object here. This is the function I get. And I get it with this following lookup. First, we look if there's a definition of SD in the global env. If there isn't, then we look in the stats package, find that definition, get the function. So if I type SD is assigned 1, and I type SD, I get 1. What happened? I defined SD in the global env, and now when I look up, I find the one from the global env and not from the stat package. If I remove SD, I'm back where I was. Okay? So why are there two of these sequences of namespaces? The reason is when I call a function from the stats package wants to have the namespace in a particular way. It wants to have all the definition it knows about. It doesn't want to have your definitions polluting it. So when the SD function is running, it is using its own set of packages first, and then it goes to the global env. I could go on, but that maybe would get tricky. So anyway, so I showed you the assignment operator, and the role of the assignment operator is to, update values. But now we know that what this means really. X is a symbol in an environment, and the assignment operator updates the binding between X and that value in the environment. By default, if we're on the console, it's the global environment. So, for instance, this little bit of code, So what does this little bit of code do? Yeah, we could. It actually shouldn't hurt either way. So what does this code do? It prints 2. So let's run through it. So we create a function that reads x is 1, okay, and assigns to x plus 1, and then returns x. So, well, that makes sense, right? X is 2, right? So we return 2. That's completely logical. Now, what should be the value of x? It should be 1, obviously. So this is a little bit tricky, so let's think about it. So there's 2 different x's going on in this piece of code. When we start running, we haven't created this x yet. So the first thing we do is we look up x. We're in an environment of this function, it's empty. So we're going to find the x that is outside. It's 1. We add it to 1, we've got 2. So we store 2 into x. This is in the function's environment, so it is a local x to that function. We return it. We're done. This one hasn't been changed. Okay. So remember this mental model. Each function has its own environment. If I store something, I store in the environment of my function. If I read something, if it's not there yet, I will find it in the enclosing environment. So the environment are chained. We look up, find wherever the definition is. Okay?
So if you combine this with the f of the f parens.
Yeah.
And basically for the function that's creating that function of x, instead of having it be a function of x, you had it be this.
Yeah.
When you called it with the second parens,
Yeah.
would you be calling that function? Would you be updating
No, you
the
still
enclosing functions environment?
you would be reading the enclosing but updating the local one.
Okay.
Which is kind of annoying also, right? Because it means a function can't change anything outside of it, right? It can only make local changes to its own variables. So that's a little bit annoying. I mean, maybe. There's a way around it. The way around it, like in R, is this other operator with these two arrows, which is called the super operator. And what the super operator does is it writes to the enclosing scope. So as an exercise, what is the value of x when we in the global environment after we run this? So what is this? We define x to be 1. We create a function that adds 1 to x, stores it in x, add 1 to x, stores it using this super assignment operator, and return x. So give you 30 seconds. Think about it. As a side note, these are common bugs in code that you see. So.
Oh yeah.
All right. So, suggestions? Sorry. Oh, suggestions? Thoughts? Oh, sorry. What is the question? The question is, in the global environment, what is the value of x? If I type x in my console, what will be the next thing that comes out? 2, 3, 3, 3. So how does this work? The first x we look up, there is no x in the local environment, so we get the global one, which is 1. 1 plus 1, 2. We assign 2 to x. The second time we look up x, there is already an x in a local environment, so we'll get 2 here. 2 plus 1, 3. We assign x here, but we use the super assignment, which goes to the enclosing scope. So we assign 3 to the enclosing scope. We return 2, and the enclosing scope is 3. Yeah?
Is there a way to simultaneously update both environments?
No, you can't. You have to just do it.
Can you update like multiple parent environments from your local?
No, you always
have to redo it in the
yeah. And the reason you don't want to do that is that it could get messy. Well,
I
yeah.
can see how that would get really messy really fast.
Yes. All right. So we've seen environments and we've seen functions, and both of them together, that's the basis of R, right? You need environments for function, you need functions for anything. So on top of that, what R adds is a bunch of data types. And the data types are data types and data structures. So the data types are double, integer, character, and logical, roughly. There's a couple of more, but let's just ignore those. So what is a double? Double is a floating point value, 1.23, da, da, da. An integer, they are, negative or positive, nothing too hard. Logical, it's either true or false, or actually NA. And character is a string. So here's an example. I say type of the number 1, and it says double. I say type of 1, and in R, in order to say integer, you have to say capital L. Why? I don't know, ask them. You can say, is this a number? Is numeric, and it will say true regardless of it's an integer or a double. And is logical, so on. So these are your base data types. Then on top of that, every data type has a missing value, an NA. So every data type has an NA. So if I create a variable x, I can store I can store an NA into it, and I can check the type of my NA, and it says, oh, this is a double NA. I can check the type of, if I just type NA, it says logical. So each NA, each missing value has a type, and it's the type, of the data structure in which you're storing it.
So it doesn't do anything under the hood to try and work out the default type based on what's passed to it. So assigning integer values to things that don't have any decimal.
By default, it will not. So by default, everything is a double. If you want it to be a non-double, you have to put an L. That's very explicit. It does do some interesting things. So if I say type of NA plus 1L, so I know that the type of NA is logical because if it doesn't know better, that's what it will do. But if I add that with an integer, what do I get? I get an integer. What is the value of 1 plus NA? Guesses? Yeah. All right. So this is perhaps the biggest departure that R has from things like MATLAB, for instance. A lot of scientific computing systems do not have support built in for missing values. Missing values are essential for statistics. You need them. If you don't have them, it's really painful to sort of fake them up. Because what you have to do, if you don't have a missing, you have to pick one number and say, this will be my missing. And then you have to check that number, and it becomes really super messy. So how do they do this? Well, for each of these data types, what R does is it steals one value. It steals the lowest integer. It steals one of the not a number floating points, and so on. So for each data type, there is one particular value that has been chosen as being the NA, and this is the one that R will use. So basic data types. What does it matter if I use an integer or a double? Well, there's two things, or three things. There's space, precision, and range. So with integers, you can represent values up to 2 million. That's a big range, but probably not big enough for all applications. The integers are encoded in 32 bits, whereas doubles are encoded in 64. So doubles take twice as much memory. Doubles are floating point values, so they can represent much larger range of values, but multiplication operations on values that are very far apart can lose precision. So, like there's all sorts of trade-offs you have to worry about this. In general, everything by default is double. The only default that is not double I know of is when you say you give ranges from 1 to 10. So this is actually, if I type off, it should be integer. Yeah, that's the only place where the default is not to be a double. And it kind of makes sense because you're saying, I want values from 1 to 10, and why would you make these doubles? All right.
Specify a fractional step size. Will that change that for
Like, so? No.
No, with the colon operator, the 10 and the 0.7.
Uh,
Or does that go?
So there's another way to give step size, but with this notation you can't. I think that's the only thing you do. And what it does is just it drops that thing. It turns them into integers.
However, if you do a double for the
From 2 and then you have a step, yes, you can. Okay. All right. So these are the basic data types, 4 basic data types. But you never manipulate things of these things by themselves. You always have them in data structures, and R has basically, most of our data structures are vectors. Environments are an exception, but everything else is a kind of vector. And the other thing that R does, which is interesting, is that all operations are vectorized. So they work on vectors. So if I can create X and Y, these are vectors of 3 values, and I can add them and multiply them, and R will add all of the elements of these vectors. So it does all of that looping for you, which is quite convenient. And almost all the operations work on the entire vector. One exception, for instance, is the if statement. The guard of the if only wants a scalar. Everything else is fine with vectors. So the things you can do with vectors are you can access using subsetting operations. So you have the square braces. The double square braces are used to access a single element. The single square braces can be used to access ranges, and we'll see more of that. You can ask what is the type of a vector, you can ask its length, and you can get its attributes. More of that later. So the simplest kinds of vectors are atomic vectors, and they are homogeneous. What that means is every value in the vector is of the same kind. So for instance, this is a vector of integer, this is a vector of strings. Can't mix and match. They have to be of the same kind, homogeneous. They can have multiple dimensions. One dimension is the basic atomic vector. 2 dimension is a matrix. Multiple, more than 2 is called an array. I can assign 2 elements of a vector using the assignment operator. I can read them. All that, nothing super fancy. Note, for interest, that this square bracket arrow is a function itself, and you can redefine that function, like everything in R. Right, so you can define matrices and arrays. So here's a matrix. A matrix, I say, what are the values? 1, 2, 3, 4, 5, 6, with 3 columns. 1, 2, 3, 2 rows. 2 rows. I run this. This is what prints, right? It's a matrix, 6 values. As a side note, this notation here is the notation you can use to get that part of the data structure. So if I type, come on. if I type A, comma 1, I get numbers 1, 2, comma 1, 1, 2, right? So I can grab a slice out of that, subset it, extract it, and I get a new vector that I can use. If I create an array, so here it's a three-dimensional data structure. 2, 3, and 4 are the dimensions, and here is how it prints out. You see there's like 1, 2, 3, 4. Yeah. All right. So, interesting thing. So I said that matrices are, and vectors in general, are homogeneous. What happens if I try to assign something of a different kind into one of those? Well, what happens is I get a coercion. So let me show you this. So was X defined? So yeah, X is not interesting. Let's do A. A, yeah. So A is a matrix of integers. Is it a matrix of integers? Yeah, yes, it is. So A is a matrix of integers. I will store a string into it. What will happen? So in most programming languages, what would happen is you will get an error. The system said, you're doing something that makes no sense. Go away. Of course, in R, that's not what happens. R is very happy. Thank you. Right? Good. So what has happened? Well, now I have a matrix of strings. Right? What did R do? Well, it did a coercion. It said, well, I have a matrix of one kind, and I'm trying to store another kind. I have to pick some kind that can store both. So let's see. A string, I can't really turn into an integer. That makes no sense. But integers, I can just put quotes around them, and that'll work, right? So that's what it does. In more formal terms, what it does is it coerces in that direction. If I have logicals and integers, I get integers. Integers and doubles. Anything and character. All right.
So if you have pretty gnarly array, maybe like a video.
Yeah.
So you got sheets of pixels.
Yeah.
So maybe like large file.
Yeah.
If you have that represented as an array in R and you want to add, quote A, quote, is it gonna run through the entire?
So the typical, really annoying bug is code where you have 100 megabytes of integer data, and by accident you assign to it and you forget to put a big L after the number, and suddenly those 100 megabytes of integer gets converted to 100 megabytes of doubles, and probably something will go bad later on, most likely. So if we have our array A, now if I try to store an integer or a double back into it, what would happen? Well, I'll give it to you. What happens is nothing. That thing gets converted to a string, because you can't convert the strings back into numbers again. So even if now there's only numbers in it, we're in string land and we're stuck. So that way, yeah, it's monotonic. It always goes towards the bigger types. And you can think about it in terms of bigger types, because logical, they have only 3 values, integer has 2 million on each side, double has many more, and character is kind of unbounded. You can have strings of any length. Okay. So the other thing that R does really well is subsetting. So, come on. I have, all right, lost my cursor. So here are all valid ways to access data in an array. In this case, it's a matrix. So I can say A1 colon. What does that mean? Give me the first row. entire first row, and you get a vector out. I can say, A, from 1 to 2, give me the first 2 rows, or whatever range I set. And this one is fun. It's give me the first 2 rows and the second and third columns. Little square. So if you print, the first thing we did gives me back a row. So that's 321. That gives me back a row, 1, 2, 3, 5. Then the second thing we did gives me back two columns. I have to make this bigger. We can't see both sides. So this one said, give me 2 rows. I get 2 rows. And this one gives me this square here, 3, 4, 5, 6, which is these values here. And then, okay, then we do something more fun. So then we take our array A and we turn it back into an integer array. We get it AA. And we can create a matrix by simply setting the dimension on it. So this creates a matrix, 2, 3. So let me just show you how this works. So I take, so this one, come on. I'm doing something wrong, come on. So this one, so AA is an integer. So A was all of these. So if you look at it, A was a matrix of strings. When I do as integer, it turns it into a vector. It forgets its dimensions of integers. Now I can do AA, and it's the same thing. Now they're all integers, and yeah. And now I can set dimensions to it. I can set dimensions. Okay. And now AA prints again as a matrix. And now I can do interesting things. So the R really shines with the subsetting operation that it has. So here I'm going to say, give me the first row of A and the columns of that first row that are larger than 1. Their values are larger than 1. So if you look at this, the first row has 3 values, and the larger than 1 values are 3 and 5. So 3 and 5. Oh, I'm getting strings. Oh, because I was accessing A and not AA. So let me do that. 3 and 5. So that's pretty cool. So you can essentially have any predicate here that returns to you a vector of Boolean values. And these Boolean values will be used to select what you want. So let me explain what I mean.
So in that call you just made,
Yeah.
you were subsetting from AA, but you asked for rows in A in the first column.
Yeah, I can do that too.
But so A is strings, right? Why didn't you get an error when?
Because R is sneaky. It knows that this is a relational operator defined over integers. This is an integer. This is a string. So it says, okay, what if I tried to interpret this as an integer? Maybe it'll work. If it does, then it gets a value. If it doesn't, it gets an A. Yeah. So if I type A1 larger than 1, so just this expression, this is a predicate. I'm saying, what are the values that are larger than 1? And it says false, true, false, true. False, true, true. So that's a Boolean vector, right? And so I can store that Boolean vector into, say, B. And now I can say A1 of B. That's the same thing. 3, 5. If I want the numbers, I say AA. So what is going on is that the subsetting of R lets you put ranges, lets you put Boolean vectors, lets you put lots of things that will give you, that will extract data out of vectors.
Does it convert the Boolean vector, right?
Yeah.
Does it convert the Boolean vector into a vector of integers, like
No. So what it does? So imagine that. So these are indices. Imagine that this is index 1, index 2, index 3. And it's just saying, ignore this index 1, keep index 2, keep index 3.
Yeah.
So we have a row that has 3 entries, 3 indices, and I'm keeping those.
So for Boolean vectors, the position is implicit.
So
and for positional vectors, sorry.
For numeric,
for
it
numeric
is
vectors,
yes. So I could have said the same thing. I could have said 2, 3, right? And I get the same value. So 2, 3, 2, 3, same thing. Okay. So, all right. Moving along. So we've gone through vectors. The other data type that is interesting in R are lists. So we mentioned lists earlier. So what is a list? A list is like a vector, except it is heterogeneous. So you can have different things in a list. So here is a list. It has the number 1, it has the string high, and then it has a vector. And a list can also have another list in it. All right. So what else do we have in R? So there's one thing that is interesting, but I will just touch on it. There's the notion of copy on write. So in R, values that you pass into a function are never modified, they're always copied. So let me try to explain this. Imagine I have a vector x. X is 10 megabytes of data. I have a function that takes that vector and updates something. If I call that function with x as argument, I will not change x. X will be the same. It will be the same as before. What I change is internally, I create a copy of x and I modify that copy. And that is really important because not everybody knows that, and it changes things a lot. So why does it change things? Well, because sometimes you think that you changed a value, but no, you didn't. You have to return that value out in order to see those changes. And here's a fun little piece of code that uses the prior package. So we'll install that real quick, or maybe it is already installed. All right. So here's what the code does. The first thing the code does is it creates capital X, an array of 10 million entries, 10 million integers. Somewhat big, not too big. Then we call object underscore size. So what is the size of X? How much memory does X take? It takes 40 megabytes. Okay? So the next thing I do is I take X and I put it into Y. All right? And I say, hey, object.size, what is the size of X and Y? Guesses? 80? 40. What happened? Nothing. What happened is X and Y point to the same piece of memory, It is only when you update it that R will create a copy. This is called copy on write. So, for for fun, if I store 11 into Y, so now I updated one of them, what will be the size of X and Y? Sorry? 80? I heard 80. No, it's 120. Why? Because we created an array of integers. We forgot to put the L here, so this is a double. It has doubled the size of that 40, so that 40 became 80, total 120 megs. Isn't our fun? All right. I have like 8 minutes or so-ish, 5 minutes, I have been told. So the next bit of R that you need, and I think that's the last bit you actually need, is attributes. Once you've seen attributes, you've seen the whole core language. So what are attributes? Attributes are little bits of metadata you can add to an object. Explanation. Here's a vector y. It has value 1 to 10. Nothing special. I can add an attribute, like my att, and say, hey, this is a vector. So if I do this, so I run the first line. What is y? Y is a vector. Now I set its attribute, and what happens next is, if I query, y is still the same vector, but it shows, hey, you've got this attribute, and its value is, this is a vector. So anything can be given an attribute. So for instance, I can have y be just the number 1, and then I can set that attribute, and if I print y, it say, hey, y is still number 1, but it has that attribute set to it. You can query attributes and all that. Why are attributes important? Because attributes are the key to implementing objects, to implementing all sorts of extensions to the language. Let me skip this. So there's some amount of fun, but let me skip this to how can we use this together. So once we've seen, so these are all the building blocks, and now we can start building things on top of these. So I will show you one thing we can build using R, and that thing is a factor. Do you know what factors are in R? So factors is a representation of data which is where repeated values are, which uses a compact encoding. So I'll show you a factor very quickly. So I can create a factor with, if I have a vector of I can't even type name, whatever. So it's a vector of strings. Yeah, I've got. Somebody should tell the RStudio folks that their string expansion stuff sucks. Yeah, but they're not here. All right, so if I print it, what do I get? Well, I get pretty much the same thing, except like these strings are not quoted. So what is happening? So, and then I have this levels thing. So behind the scene, what is happening is that the vector is recoded to be just integer values. The integer values have a meaning. So like 1 is the string hi, 2 is my, 3 is name. So if I wanted to show you this, let's see, would I do this? Would it work? No, so if I do as integer. Right, so this is the actual encoding of the vector. So you started with a vector that had lots of strings, lots of repetition, and the factor creates this cool, compact set of numbers, and then there's a table of all the attributes all the values of these that is hanging off. So what I wanted to show you is, factor is not built in the language. It's built on top of the mechanisms I've shown you. So we can build our own implementation of factor in 5 lines. It's not really hard. So let's call it simple factor. And this is the simple factor function. What does it do? It takes a vector, x, and it calls unique. It says, anything that is repeated in x, throw it away. Give me just unique values. Then it turns that into strings. If they were strings already, that's fine. If they're not, we've got them as strings. And that it calls the levels. Then it does a match. So match takes the original vector x and the levels and gives you a new vector that says, this level, where does it occur in that vector? So that's f. And then we set the attribute levels of the vector f to be these strings. We set the class of f to be simple factor, and we return f. And this is the implementation of factors in R. So this is like something you see everywhere, but it's like 5 lines, 6 lines of code. But the actual implementation is a little bit longer because they have some special cases, but this is roughly it. So let's see. So now we can have our own factors, and we can create ourselves a vector and call the factor method, it's a simple factor method, and print it. So, I'm getting ahead of myself. That was not supposed to happen. It's actually, let me just do this. I've already solved the problem I wanted to show you. That was, so let me just do this again. So, right. So if we call simple factor, what we get is this encoding, very compact encoding, these levels. So I can do that with strings. That would work as well. So if I say x is the vector of strings high and whole, it should give simple factor should return 1 and 2. That's my guess. Yeah, 1 and 2. So it returns 1 and 2, and the levels are high and whole. All right, but this is not pretty, right? This is not pretty. What you want is a pretty printing function, and you can do this again in 5 lines by, no, actually more, a little bit more, by writing this print.simpleFactor function. And what it does is it creates a copy of your vector. It unmaps the level into their values, prints the level, and is done. So you can read this, play with this. I think I ran out of time. So I had other things that I wanted to show about objects and stuff. You'll see that in the notes. And the object-oriented part of the class will be covered by Kylie. And that's all I had for you. Thank you very much.